How's it going, guys? In this video we're going to go over the law of conservation of energy. This is going to be our last video in the thermochemistry series. So first off, let's just jump into the concept. The first law of thermodynamics is the law of conservation of energy. Basically what it states is that the total change in energy is equal to the sum of the heat and the work transferred between the system and the surroundings. So in a sense, if one goes up, the other goes down. If one goes down, the other goes up. And also we can calculate it as delta E equals Q plus W, which is heat plus work. So another way to look at this is this kind of diagram, which I feel like a lot of people have probably seen before, but basically what it is there's a system, and everything that's not the system is considered the surroundings. So basically if the system is heated, then that would be endothermic for the system, and the surroundings would get cooler and the system would get warmer. And then the opposite would be exothermic. It's giving off heat, so the surroundings would get warmer and the system itself would get cooler. So for example, an example of an exothermic reaction would be those pocket warmers, the hand warmers. When you crunch them and then you initiate the reaction, it's an exothermic reaction. It's cooling the inside the system is cooling, so it's giving off heat, and the heat is what warms your hands. And the opposite is true of those ice packs that people pop before for sports injuries and stuff. That is initiating an endothermic reaction, which is making the system itself warmer and giving off cold. So from there we're just going to jump in. I'll put this to the side and then we can do some problems. I'll try to start off with an easier one, and then we'll kind of work our way to the more difficult ones. So I think one of the most basic types of these problems can be this. Find delta E when a gas absorbs 18 joules of heat and has 13 joules of work done on it. So first off, we can just really quick assess this formula here. Delta E equals heat plus work. We're trying to find delta E, so we're just going to add these two numbers. It's that simple. 18 joules of heat plus 13 joules of work, and we're going to get 31 joules. It's going to be our delta E. From there we're going to have find Q, or heat, when 72 joules of work are done, or is done. Yeah, I think that should be is done on a system, and its E is increased 61 joules. So first off, we'll jump right back to that formula that we used before. Delta E equals Q plus W. And from there, we're just going to plug in our numbers. What do we have? So first off, we have the 61, the increase in 61. So we'll say 61 is equal to Q, because that's what we're looking for, plus the work, which was 72 joules. 72 joules. So from there, what we can do is we can subtract from both sides 72, and that's going to give us Q is going to be equal to negative 11. So now we're moving on to number 3. We'll have this one be a little bit more complex. Okay, so consider the following reaction. in a vessel with a movable piston. Let's see. X grams plus Y grams. I'm sorry, not grams. X gas, Y gas yields Z liquid. So as it occurs, 1,185 joules of heat are given off. Okay, so from there we'll have piston moves down and the system so this should be because it loses 1,185. The system, okay, surroundings do 623 joules of work on the system. Okay. What is delta E? All right, so we can just kind of run back to this really quick, just for kind of a reference point. It said that here the surroundings do 623 joules of work on the system. So what we're going to have there, we can always go back to this here, Q plus W, and from there we can have, so as it occurs, it loses 1,185 joules of heat, or it's released. So what we're going to have is a negative 1,185, and from there we're going to have plus, because it's our heat plus work plus 623, and these are both joules. The thing you really want to be careful with is knowing when you should have a positive and when you should have a negative. Depending on what you're looking at, it's usually always going to be based on the system. So if the system's losing, it's exothermic, it's going to be negative, and the reverse is happening if work is done on it. So that's why we have a positive 623 and a negative 1,185. So what we're going to get there is we get negative 562 joules. It's going to be our delta E. All right, so we'll keep moving with these, and let's see here. Calculate delta H and delta E at 25 degrees Celsius. For the reaction that takes place when an oxyacetylene torch is used. Okay, so here we have C2H2 gas plus 5/2 O2 gas yields 2 CO2 gas plus H2O gas. Okay, so from there, basically I think the first step would be to find delta H. Want to find delta H values. So from here, our delta H values can be, a lot of times they're found, like you can find them in tables or whatever, depending on what you're using here. But the next step will be find the delta charge so that we're looking for the change in number of moles of gas as reaction proceeds. This one I'm kind of just mapping out some of the important things to know. There we go. Our R value for this is going to be 8.31 joules per mole times Kelvin. That's anytime energy units are involved. And then finally, substitute in delta H equals delta E plus delta Ng delta RT. So that looks a little bit confusing, but I think it's probably going to make sense once we start plugging things in. So first of all, our delta H values. In this case, it says calculate delta H and delta E at this and this. Depending on what method you use to find your delta H, this one I looked up ahead of time so that it wouldn't be a pain, because we already discussed how to find that in previous videos. So here we're looking for the delta E minus, and we're going to have negative 0.5 mole, which is our change in gas, because what do we have? We have the 5/2, and we have the 1 here assumed, 2 here, and 1 here. So that's kind of our change. Really what we're looking at, since everything is gas, the total net. So this is like equivalent to 2.5, 1, and so that's 3.5 in total. Then we have 3 over here, so the difference is 0.5 mole. So that's where we got that. And then we have our R value. So 8.31 times 10 to the negative 3. That's going to be kilojoules over moles times Kelvin, just because we converted it there to kilojoules instead of joules so that it would be consistent across. And then we have our T, which we're given up here is 25, so we have 25 plus 273 is 298 Kelvin. All right, cool. And now we can kind of just solve across. So basically what we're going to have, and we get delta E is equal to negative 1255.5 kilojoules plus 1.24 kilojoules, which is what we got on this side. And then from there, our final answer should be 1254.3 kilojoules, and that should be negative. All right, cool. So that last one got a little bit messy, I think, but basically what I tried to do is map out some of these steps, and then from there move forward. So yeah, I think that this last one here is probably as tricky as these the conservation of energy problems can kind of get, at least from what I've seen. So I think that if you're more comfortable with obviously the most complex ones, then you should be in good shape. But yeah, I think the most important things to keep in mind are these two things right up here. So yeah, I hope this helps someone.